Alright, this is section 3, using Newton's laws. So this is an opportunity for us to actually take what we've learned with the 3 Newton's laws and actually apply it to things that we see in everyday life. Alright, so the first one is actually car crashes. And car crashes are a great way to actually see the application of Newton's first law in action. And so we call that, of course, the law of inertia is Newton's first law, right? And so the first law allows for us to see, an object in motion stays in motion until an unbalanced force acts upon it. Well, with a car crash, if a car is traveling, for example, at 50 kilometers per hour and hits something head on, what happens to the car? It crumbles, it slows down, it stops, and it does that in approximately like 0.1 second, so very, very quickly. What happens though is that someone who's not wearing a safety belt continues to move forward at the same speed that the car was traveling. So they continue to move forward even though the car has officially stopped. So they haven't had an unbalanced force act upon them, so they continue to move. So what happens is that even though at 0.1 seconds the car has stopped, about 0.02 seconds though, the person in the car will stop because they're going to hit the dashboard, they're going to hit the steering wheel, they're going to hit the windshield, whatever, or if they're in the back seat, they're going to hit the back of the seats. That's typically where you're going to see the first law in action, because they're going to continue to move until an unbalanced force acts upon it. Now keep in mind though that you're going to see the law of conservation of momentum happening, that when cars crash, momentum is transferred. It's transferred from one object to another. You're going to transfer your momentum to an object. The car is going to transfer its momentum to another object. Remember that momentum doesn't change unless it's mass, velocity, or both change. It just transfers from one object to another, and that's called the law of conservation of momentum. So just keep that in mind. We kind of studied that last chapter, but it kind of goes along with this. Now, how do we prevent from car crashes from that object in motion staying in motion? How do we prevent that from being so bad? There's a couple of ways. One is our seat belts. The purpose of a seat belt is not to hold us in, strap us in so much that we don't move. That 50 kilometers per hour that we were going before, if we wanted to basically stop us, we would that force would be 14 times the force of gravity in order to stop us. And if we did that, that would hurt us pretty darn bad. So what a seatbelt does is that it loosens a little bit to restrain the person, but it basically slows the person down. It doesn't completely stop us, but it allows for us to basically slow us down so we don't slam into the things in front of us as hard. So it reduces our force. So it allows for us to still go forward, but it reduces the G-force. It reduces the ability of us being thrown from the car. So it's not meant to restrain. It's not meant to hold us into the car, strap us down, like the whole, I think of it like, don't duct tape us to the car. It's meant to just reduce the amount of, instead of throwing us completely forward into the dashboard, it's meant to just slowly jolt us into the dashboard. So you're still going to hit the dashboard, you're still going to hit the things in front of you, but just not with as much force. It's to reduce that. So if you're going a slower speed, you're not going to hurt yourself as bad as if you're going a faster speed. The other thing is now cars are equipped with airbags, so if you are thrown forward, you can have a cushion, kind of like a pillow. It sounds so nice, but of course this is not a nice thing depending on how fast you're going. So you have an impact. What happens with an airbag is that there's a chemical reaction, like in the dashboard, that actually comes up. It produces nitrogen gas. They're called airbags, but it's not truly air. It's nitrogen gas. Nitrogen gas is produced within the steering column or wherever there's an airbag. It fills up the airbag, and there's little holes in the bag itself, and so as soon as the bag fills up, it's released out, and that's why it expands rapidly, and then it deflates just as quickly as the bag basically is filled. Okay, so that's basically car crashes. Now we're going to talk about something called free fall. So another example of Newton's laws in action. So free fall. Free fall. I think of that song. And we're free. Free falling. Okay, I'm done. Sorry. This is where all forces except for gravity are basically ignored. So when you're falling down, and all we look at is the g-force. So the g-force, of course, is 9.8 meters per second squared. G-force is g, and it's called the acceleration due to gravity, and it's equal to the net force on the object, meaning that the only thing we're looking at is gravity. So when you jump out of a plane, you're free falling. Now, we don't ever really free fall, because when we fall, we have something that's pushing back up at us. There's a friction-like force that opposes free falling, and it's called air resistance. So it's a friction-like force. It moves through the air, and it opposes things that are falling. It causes things to fall with different accelerations, so that's why if we drop a piece of paper versus, a bowling ball or something, it causes things to fall at different speeds. It depends on the size, shape, and speed of objects, and like I said, that's why different things fall with different speeds. Okay, terminal velocity. Terminal velocity is the highest speed a falling object will reach. So if you jump out of a plane, this is the highest speed you will reach when you fall. And again, terminal velocity will depend on the size, shape, and speed of an object. Oops, sorry. Okay. Terminal velocity, sorry, I lost my spot with that. As an object falls, the downward force of gravity causes the object to accelerate. As an object falls faster. So what happens is that you're falling, okay, g-force goes down, and then of course you have air resistance, it goes up, okay, and then eventually those two equal out, and then you get the speed, and that's your terminal velocity. So we're going to show you here in a second a little tiny clip of a skydiver, and it shows this in action. So watch that, and then we'll come back.
When a skydiver jumps out of a plane at 3,000 meters, her speed goes through some big changes. So what's happening to the forces as you fall through the air? The force of gravity is always trying to pull us towards the Earth. Before the skydiver jumps, the floor of the plane provides a counterforce which balances the downward force of gravity right up until the moment she steps out. Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance. Eventually, the upward force of the air equals the downward force of gravity. When forces are balanced, the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating. She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea. To slow down, the upward force needs to be greater than the downward force. When the parachutes open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down. Because she's slowing down, Air resistance decreases until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea. As she hits the ground, there's a thumping great counterforce from the Earth, which decelerates her very quickly. So for skydivers to land safely, they need to understand forces and use air resistance to slow themselves down.
Alright, now we're back. Another example of Newton's laws in action is weightlessness. And so you've probably seen pictures of astronauts and equipment floating in outer space, and you've said that they are weightless. And so you say that, they have no weight and that there's no gravity, but are they really truly weightless? Okay, now we're going to break away here again, and I'm going to show you a little clip of the idea of being weightless, and then we'll come back and we'll talk about this slide here about floating in space and being weightless.
Have you wondered what it would be like to be an astronaut floating around in the space station?
But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating?
No gravity.
No gravity.
Zero gravity.
There's no gravity.
Gravity.
The stuff that holds us to the planet when we spin doesn't happen up there.
Gravity holds you down, so in space there's nothing there, so you just float.
There's no gravity in space.
No gravity, or there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So, where would the space station fit in this picture?
Can you make me a roughly to scale model of the Earth and the moon? And then we're going to position the space station in there. So about like that?
Yeah, about there.
Closer, maybe. About there.
Are you ready to see the real distance? What do you reckon?
Oh, okay.
It's actually about here, maybe a little further.
I think we were wrong.
Now, if the moon is here and the Earth is there, whereabouts would you put the space station?
Somewhere around here.
Further here?
Midway.
About halfway?
Yeah.
Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. Are you ready for the real distance? The space station is right about there.
That close.
Oh, okay,
Right there.
that close.
Wow.
We're not good at this game.
The space station is actually only about 400 kilometers away. So if you're in Sydney, it's a little further than the drive to Canberra.
But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
There's not much. They float. We've seen them.
Well, clearly there's not. They're floating around.
I know they float. And the question is why?
No idea. I'm really confused.
Well, in truth, the force on the astronauts is almost as much as the force on you. So then, why are they floating while you're stuck here?
The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them.
If the Earth didn't put a gravitational force on them, they would fly out into space.
Sure, yeah.
Right? So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they...
They would still feel weightless until you smash into something.
Okay.
So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
Okay, so we're back. A space shuttle in orbit, as you saw, is going around the Earth, and so instead of actually the astronauts being weightless, they are actually just falling towards Earth, and so because they're falling towards Earth, they still have gravity. It's just because they are falling towards Earth and accelerating towards Earth, they're free falling, and so they're giving them the sensation that they are weightless. So it's not that they're actually truly weightless, it's just that they have that sensation of weightlessness. So they're floating in space. So they're not truly weightless. In fact, they have weight. In fact, people that are on the space station actually have about 90% of the Earth's gravity. So they're not truly weightless. So it's kind of interesting. Alright, now for something else. Something called centripetal force. According to the second law of motion, when a ball has centripetal force, the direction of the net force actually is applied towards the center of a curved path. So if you have a circular path like a road, the net force is always towards the center of that, and that's called centripetal force. So when you have your highway or whatever, and you need it to go around that curved path, what keeps it on that curved path is centripetal force. So, centripetal force is the frictional force or traction between the tires and the road surface. Anything that is moving in a circle is doing so because of the centripetal force that is accelerating it towards the center. So the centripetal force is what keeps basically the traction and the tires going around the center of the circle. So you have your centripetal, so you have your rolling friction that is between the tires and the road, and the force is what keeps it so it'll go around the circle. So you have all those things in play that makes it so you can do your turn. Alright, another example of Newton's laws in action. Oh, sorry, forgot about this. Another example of centripetal force in action. You can imagine whirling an object around your head, and so Earth's gravity acts in that way. So here's an example of centripetal force. The moon would be the ball where you have the string, okay, and here's you, okay, and so centripetal force would be the string keeping the moon circulating around the Earth. So gravity, it would be the example of this centripetal force causing the Earth to go around the moon to go around the Earth. Okay, next, probably an example of the third law here would be rocket propulsion. For every action, there's an equal and opposite reaction. So, for a rocket, rockets burn fuel, so the rocket engine exerts a force on these gases, causes them to escape out of the back of the rocket, so that in turn the rocket pushes it forward. So action, reaction. So rockets are a great example of those laws in action.